So we're going to deal with the type 3 ionic compounds, and this is essentially polyatomic ions, which we've learned of in the last module. And polyatomic ions is just a group of atoms, typically covalently compounded together, covalently bonded, and they have an overall ionic charge. This list goes through some of the common polyatomic ions, and some of them you may have heard of. Acetate, bicarbonate, so sodium bicarbonate, typically used in cooking and baking, carbonate, chlorate, chlorite, sulfites, for those of you that drink wine, if you're old enough, the sulfites, some people that cause headaches, nitrates and nitrites, a lot of these are preservatives in meats, and some of that bright red color that you see that looks really nice in a grocery store is actually a result of these types of preservatives being added, and actually artificially gives it that reddish color. Perchlorates and thiocyanates. The main ones that we deal with in our dealings are simply going to be typically acetate. Carbonate is a very common one. And it's pretty much the ones you would see on the back of a bottle of water. So nitrates and nitrites, and the sulfates and sulfites. Also, two common cations, polyatomic cations, are the ammonium and the hydronium ion, and we're going to deal with these quite a bit, the hydronium ion especially. As far as really understanding the polyatomic ions, the majority of the work you're going to have to memorize these. That's pretty much what it comes down to. There are some little hints that you can go through to try to determine one from another, but really what you're looking at is trying to memorize a few key compounds. The carbonate is specific. Chlorate, you're looking for the sulfate and the nitrate. So these ones specifically you're going to want to memorize, and from these you can start to derive some of the others. We can also deal with the phosphate as well, if it's on here, phosphate, and we can see the relationships of the naming with these main ones. So if we take phosphate, for example, we're going to deal with the compound PO4 3-, and this is given the name phosphate. And we can see there's a couple of ions that are related to it as well. One of the things we'll notice is that we actually, if we lower the number of oxygens on it but still keep the charge, we go from a PO4 to a PO3 3-. This name is given as phosphite. So if we have the highest oxidized phosphorus, we're going to call that phosphate. So that's with 4 oxygens on it. If we decrease the oxygen once, we're going to call it phosphite. And we can see that relationship with any of them. We see sulfate, and if we go to sulfite, the charge is the same overall, but there's 1 less oxygen on it. And we go to nitrate, same thing. We have 3 oxygens on it with a 1- charge, that's nitrate. We go to 1 less oxygen, NO2-, and we call that the nitrite. So that's the basic relationship between reducing the number of oxygens. The next one we can talk about is when we add a hydrogen in front of it. So if we talk with, for example, the carbonate ion, which is a 2-, and what we're going to do is we're going to put a hydrogen in front of this, and we're now going to call this HCO3 1-. So there's a reduction in the charge and a hydrogen's in front of it. So the original ion was called carbonate, and when we put the hydrogen in front of that, we can call that bicarbonate. And this is the one you may have heard of in your cooking or baking, is the bicarbonate. They're related to each other. The other name for that is just calling it hydrogen carbonate. And it's a same name, carbonate, overall. But you can see that relationship as well, and that occurs even with the phosphates. So if we have, for example, phosphate, and we look up above, we can see that we have hydrogen phosphate, and that can also be called biphosphate. And the last relationship that we're going to deal with is with the chlorates. And specifically we're going to deal with the perchlorate, which is the Cl O4-, We're going to deal with the chlorate, which is one oxygen lower. We're going to deal with the chlorite, which is one oxygen lower than that, and then we're going to deal with the hypochlorite, which is the oxygen one lower than that even. And the charges all remain the same, it's just the number of oxygens attached to the chlorine are different. So this is a relationship. In this case we called the first one the perchlorate. The second one we're going to call chlorate, and this is the one that you want to memorize. The chlorate is always the base one, much like the sulfate or the nitrate. So the chlorate is the one you want to memorize, and everything can be determined based off of it. We reduce the oxygen by 1. We now turn this into a chlorite, and if we reduce this by even one more oxygen, keeping the charge the same, this is now called hypochlorite. Hypochlorite is typically the bleach or the material that's actually used in your pool. If you're going to use some chlorine-based material, usually this is it. Now keep in mind that this series also occurs for both the bromine and iodine. So in the case of bromine, instead of ClO4, I'd have BrO4, and that would be called perbromate. I would have BrO3 minus, and that would just be bromate. And then I have bromite, and then hypobromite. And as far as naming goes, it's as simple as determining what the counter ion is and what the polyatomic ion is. So for example, if we wanted to deal with a compound between sodium and carbonate, I want to have a compound that has sodium in it, and I want a compound that has the polyatomic ion CO3. But remember, this entire thing carries the 2 negative charge. So if I have sodium that has a +1 on it, how many sodiums do I need to counteract the 2 minus charge of the carbonate ion? Well, I need 2 of them. So I would write that as Na2CO3. Now notice I didn't write the brackets there, but it's always implied that those brackets are there when you write this. Let's try a similar one with potassium and sulfate. So I want to write something with potassium, and I want the sulfate ion. This is also a 2 minus. So the potassium has got a +1. It's in group 1A of the periodic table, has a +1 charge. How many potassiums do I need to create the sulfate? It is 2 of them, so I'm going to create the sulfate like this. Now the brackets aren't needed, but just remember, if you were to see this, you should start to understand that this is a polyatomic ion, that these are the metals and the rest of it afterwards is a non-metal, and that this makes up a group that becomes a polyatomic ion. In terms of naming, it's the same as we would do with any other ionic compound. The metal comes first and it's the full name, so in this case it's potassium. And we would just write out the name of the polyatomic ion. In this case it's sulfate. Or if you want to use the pH instead for sulfate, that's fine as well. And we'll try one more. Let's say we want to make a compound between aluminum and phosphate. We want to determine the charges. On aluminum it's a +3 charge. On the phosphate it's also a +3 charge. In order to make a compound, I only need the 1 aluminum for every phosphate molecule that I have, for every polyatomic ion. Again, I'll write the brackets around, but most times you're not going to see that written in brackets. You're going to see it written as this. Recognize that this is the metal. Overall this has to be an ionic compound because these are nonmetals, and recognize that the grouping means it's a polyatomic. You'll then have to memorize this and realize that this is a phosphate group. To know the charge, aluminum is in group 3. It automatically has a +3 charge, which means that your phosphate group has to have a 3 minus charge overall on it. In terms of naming, we will call this aluminum, which we would find from the periodic table, and we would just use the phosphate as the counter ion name for it. And we'll try one last one, and this time we're going to go from the name. In this case, we're going to go with the name ferrous nitrate, and we're going to determine what the charge would be from this, what the compound would be. So from ferrous nitrate, we know that this is iron. So we look up on the periodic table and we know that we have iron with a +2 and a +3 charge. The ferrous refers to the lower oxidation state, the +2. So we have Fe2+ that's involved. Nitrate, we look up on this table, we see that nitrate is NO2-, so we know we have an NO2-. So how many nitrates do I need in order to balance this +2 charge on the iron? I've only got a -1. I need 2 nitrate groups. So in this case, I'm going to rewrite this. I am going to use the brackets this time because I have to denote how many of these nitrate groups are being used. There are 2 full nitrite, not nitrate. Oh, I am saying nitrate. Sorry. NO3, NO3. So we're using the nitrate group. Charge is still the same, luckily, so I don't have to do much finagling here. But there are 2 nitrate groups that are required for every iron group. I use the brackets to denote that I need 2 full polyatomic ions in order to actually do this. And one more for fun. So let's derive the name for this compound. So we now want to make this compound out of copper, and we're going to try this one. So from this compound, we know it's an ionic compound because we have a metal and a series of nonmetals. Hopefully the grouping in the brackets you realize is a polyatomic ion. We look up in our chart what this could be. It looks like it's a hydrogen sulfite. So just from this table alone, we know that a hydrogen sulfite ion overall has a -1 charge. The copper, we're not sure what the charge is, but if we know that this has a -1 charge, and if we know that there are 2 of them, that would mean that the copper must have a 2+ charge in order to exist with the 2 hydrogen sulfite units. On the periodic table, copper exists as copper 1 and copper 2. Since this is the higher oxidation state, I can call this cupric. If it was the lower, the +1, it would be cuprous, but in this case it is cupric. And I can call this then the cupric and just put in the name of the ion. So hydrogen sulfite. Or I could call it cupric bisulfite. Either one of those would work.